Hello everyone, welcome to China Meteorological Administration Training Center training series entitled Operational Use of the High-Resolution Numeric Models on Severe Convective Weather. My name is feihaiyan1 and I am an Associate Professor in China Meteorological Administration Training Center. Here I thanks to Xiuming Wang, Xiaoding Yu, Liang Boqi, and Mingxuan Chen. Firstly, we have a basic idea of how does numeric model work and the main characteristics of the high-resolution models. Secondly, the main high-resolution numeric models in China will be displayed. At last, we will see the operational use of the high-resolution numeric models on severe weathers such as hail, convective windstorm, and heavy rain. Before the class, let's look at the future for the meteorologists. As we all know, during the past 30 years, the numeric models have improved dramatically. Machine learning plus high-resolution models post-processing system have pushed the forecast capacity change a lot. Look at this image. The forecast will become integrated authoritative voice. We do believe for the severe weather, humans will continue to play an essential role in the forecast process, a role which demands situational awareness and requires understanding to interpret, select, blend, modify, and sometimes discard numeric weather prediction model output and statistical guidance. The numeric model is so important, so we need to know how does numeric model work. Firstly, we use the term numeric model type to refer to whether a model is green point or spectral, and hydrostatic model or non-hydrostatic. Green point and spectral models are based on the same set of primitive equations. However, each type formulates and solves the equations differently. Green point models represent data at discrete, fixed green points, whereas spectral models use continuous wave functions. Model type have no direct impact on the choice of horizontal or vertical resolution down to around 10 km horizontal green spacing. Theoretically, green point and spectral models can be of any resolution within the limitation of available computing power. However, a model with very high horizontal resolution should be non-hydrostatic, so the mesoscale numeric model and cloud resolution model are always green point and non-hydrostatic models. We all know global models have historically been spectral because the wave function and spherical harmonics in the spectral formulation form a natural mathematical basis of a spectral domain, allowing high accuracy in modeling the motion of a fluid on a sphere, such as the atmosphere over the Earth. However, global models are increasingly become green point as computer resources increased. Non-hydrostatic models are usually limited to small domains because the additional cost of computing. The non-hydrostatic terms only helps the forecast of small-scale features, requiring high resolution to resolve, and some operational centers have begun to run a global high-resolution model in real time. Let's see the main framework of the numeric model system. Very simplified model system. The observations such as satellite, radars, airplanes, and surface observations. So many materials are processed by quality control into the model assimilation systems in order to get a better initial field. The characteristics of the physical and dynamic situation of atmosphere are represented by equations influence the type and scale of features that a model may be able to catch. Then the user can get the numeric products through post-processing system. This is the very simplified display of numeric model system. In order to have more details of basic framework of numeric model system, next we will talk about three aspects: hydrostatic versus non-hydrostatic models, model resolution, impact of physical parameterization. High-resolution model always need boundary conditions which could be obtained from a variety of sources, so we just mention here but don't unfold this part later. Through this part, we hope to help you have a basic understanding of high-resolution model framework. Traditionally, the global model were all hydrostatic, which means the vertical motion equation is simplified to an assumed balance between the weight of the atmosphere and the vertical pressure gradient. That means pressure gradient forces equal to gravity. The hydrostatic approximation only applies well to phenomena which have a longer horizontal length than vertical depth. The hydrostatic model's vertical motion is diagnosed from other forecast variables, not calculated directly. This simplification has almost no effect on the prediction of large-scale phenomena and allows the model to run faster. These 5 equations are used in model to govern changes in the motion and thermodynamics of the atmosphere and are derived from the complete set of conservation laws of momentum, mass, energy, and moisture. Hydrostatic equations is here. Let's move to the continuity equations. In hydrostatic models, vertical motion is diagnosed from other forecast variables, not calculated directly. The continuity equation is used to calculate vertical motion in hydrostatic models. You cannot find the changes in vertical velocity with respect to time. On the other hand, non-hydrostatic models don't use the continuity equations directly to calculate vertical motion. Rather, they use a combination of horizontal divergence and buoyance to determine both vertical motions and vertical accelerations. Hydrostatic simplifications allow the model to run faster, but why we need non-hydrostatic models? We see on the synoptic scale, horizontal length is larger than the vertical depth, but severe convective weather usually caused by mesoscale or even small-scale features. Look at the diagram in the left, such as isolated thunderstorms. Tornado thermals belong to non-hydrostatic regions. For example, even in a thunderstorm updraft, longer horizontal length equal to vertical depth, the thunderstorm updraft can be considered to be non-hydrostatic phenomenon. But for the rain-cooled outflow that the thunderstorm produced, longer horizontal length larger than vertical depths, the outflow can be considered to be an approximately hydrostatic phenomenon, so the atmosphere is more complicated than the model describes. Non-hydrostatic models can explicitly forecast the release of buoyancy in the atmosphere and its detailed effects on the development of deep convection. To accomplish this, non-hydrostatic models must include an additional forecasting equations that accounts for vertical acceleration and vertical motion directly, rather than determining the vertical motion diagnostically. Changes in vertical motion from one time step to the next in a grid box are caused by advection terms, non-hydrostatic vertical pressure gradient force in a grid box, buoyancy, and precipitation drag. Let's look at the differences between hydrostatic and non-hydrostatic models. For example, in this situation, sea breeze, broad gentle mountain waves, frontal circulation, and so on, hydrostatic models performance good enough, almost no differences. But models run with grid spacing of a few kilometers or finer need to be non-hydrostatic. For example, boundary layer rows, MCC convective elements, and so on. Such high-resolution models characteristically predict details, mesoscale structure, and associated forecast impacts on surrounding areas. Because we pay more attention to mesoscale phenomenon, which caused severe weather, so when we talk about model type, we mainly talk about green points model. Resolution is defined here in terms of the grid spacing and represents the average area depicted by each green point in a green point model. Whether a model is considered high or low resolution depends upon the size of the domain and the scale of weather phenomenon that the model is trying to predict. A resolution on the order of 10 to 50 kilometers is considered high for a global model, while for a storm scale model, a resolution of 100 to 500 meters is considered high and necessary to resolve the internal processes of convective. This is the example of 9 kilometer grid spacing model. The main operational high resolution are as follows. Global models can reach 10 kilometers. Mesoscale model can reach 1 to 3 kilometers or even 100 to 500 meters. As with global and regional models, uncertainty inherent in the forecast can be addressed to some degree with ensembles. Global ensemble model can reach 10 to 20 kilometers, and mesoscale ensemble models can reach less than 10 kilometers. Let's review the classification of the mesoscale. Thus, the 3 kilometer resolution model can capture the 3 kilometer small mesoscale gamma phenomenon. Unfortunately, it cannot. Look at this diagram. Note that the smallest features that can be accurately represented by a model are many times larger than the grid resolution. In fact, phenomenon with dimensions on the same scale as the grid spatial cannot be depicted or predicted within a model. What grid size is necessary to resolve any particular weather feature? It typically takes at least 5 grid points to define a feature in a grid point model. It takes about 5 to 7 grid points to get reasonable approximations of most weather features. Still, more points per wave feature are often necessary to get a good forecast. The smallest weather feature that can be depicted, even within short-range forecasts, span 5 to 7 grid points. Phenomena that can be preserved in 1 to 2 day forecasts typically have wavelengths greater than 8 to 10 grid spacing. In this case, 3 km grid spacing means that the model cannot predict features smaller than about 15 km in size. Thus, don't expect accurate prediction of local flows on the scale of 15 km from a model with a 3 km grid spacing. It typically takes at least 5 times the grid spacing to define a feature in a grid point model, based at scales greater than 10 times the grid spacing. For example, this is an operational model prototype in Shanghai. Look at this on the left. The grid spacing is 9 kilometers. This in the middle, the grid spacing is 3 kilometers, and the 100 kilometers resolution is in progress. Just as sufficient horizontal resolution is necessary to depict different atmospheric phenomena, the models must also be designed with adequate vertical resolution to forecast the vertical structure and the effects of a variety of meteorological events. High vertical resolution is not needed in the middle to upper troposphere in tropical and summer barotropical conditions under high tropopause. Instead, forecasting more layers near the ground can better capture surface processes affecting the diurnal cycle, convective instability, and terrain and coastal forcing of convergence, which may deepen the moist layer and trigger convection.